Welcome to Lecture 2. If you're watching this, congratulations. That means you've made it through the first lecture and you're coming back for more. Today we're going to be talking about electron configuration and periodic trends, and that is found in Chapter 8. So last time we talked about quantum theory, and that was the material covered in Chapter 7. 7.1 dealt with the nature of light. That's where we started. We talked a little bit about atomic spectra. And 7.2 we went into detail with the explanation of the spectrum from hydrogen and Bohr's model. Then we talked about wave-particle duality. This was de Broglie's equation for matter waves. And the final section, we got into quantum numbers and orbital shapes. So this time we're going to start out with a few short review questions over Chapter 7 material, and then we're going to continue on to Chapter 8. Section 8.1, we're going to talk about electron spin and energy level splitting. Section 8.2 covers electron diagrams and the periodic table. And finally, Section 8.3, we're going to talk about trends and atomic properties. And two important trends we're going to talk about is our size and ionization energy. I showed this last time in the last lecture, but I thought I'd do it again. I think this is a very good summary of Chapter 7, where we start off with classical theory. And classical theory sort of stated that matter is composed of particles. Radiant energy, such as light, has wave properties. But there were, remember, three observations that didn't match up with classical theory. One was the black body radiation, and Planck used his theory that energy is quantized, shown here with Planck's equation, to explain these observations. Einstein used Planck's idea of energy quantization to explain the photoelectric effect, and the equation for the photoelectric effect is here. And both of these theories was that energy is quantized. Now Bohr used that theory plus the observation from line spectra to create his model for a hydrogen atom, and that equation is shown here. And de Broglie used sort of this information, these observations, these theories, to come up with his own theory that matter itself has wave properties, and de Broglie's equation is shown here. And finally, Schrödinger and Born put this all together into what we know today as quantum theory or quantum mechanics. All right, let's start with some review questions. So question 1, if an electron in the ground state absorbs one photon of light, then relaxes back to the ground state by emitting an infrared photon with a wavelength of 1200 nanometers, followed by an orange photon of 600 nanometers, what is the wavelength of the absorbed photon? So to answer this, you have to know that the energy of the absorbed photon has to equal the energy of the first emitted photon and the second emitted photon. So we'll call that E absorbed. So E absorbed has to equal E1 plus E2. So take a couple minutes and try to solve this question, and we'll come together and answer it as a group. So we have energy absorbed, energy of the first photon emitted, and energy of the second photon emitted. So E absorbed has to equal energy 1 plus energy 2. Okay, then we can, if you recall Planck's equation, energy equals Planck's constant times frequency. But we're given, our photons we're given are in wavelength in nanometers. So we can either convert nanometers into frequency, or we can rewrite Planck's equation. So Planck's equation in terms of wavelength is hc over wavelength. So now we can solve for the energy 1 and energy 2. So energy 1 equals 6.626 times 10 to the minus 34 joules seconds times 3 times 10 to the 8th meters per second divided by 1200. Now remember, we have to convert from nanometers to meters. So that would be 1200 times 10 to the minus 9th meters. So what I get is 1.66 times 10 to the minus 19th joules. That'd be the energy of the infrared photon given off. E2, we do the same thing, except we use 600 nanometers. I'm not going to write that all out. But what I end up getting is 3.31 times 10 to the minus 34. Times 10 to the minus 19th joules. And you see that that makes sense. It's roughly twice as, the energy is 2 times that of the energy 1, and the wavelength is twice as short. And if you remember the relationship between wavelength and energy, the longer the wavelength, the lower the energy. So now we can solve for the energy of the absorbed photon, and that's just these two energies added to one another. And that is about 4.97, or about 5 times 10 to the minus 19th joules. Now we can use Planck's equation again, rearrange it, and this time solve for wavelength. So E equals hc over lambda. If we solve for lambda, we get lambda equals hc over E. And when we plug all our numbers in for this, 6.626 times 10 to the minus 34th joules seconds times 3 times 10 to the 8th meters per second divided by 4.97 times 10 to the minus 19th joules. The number we get out is 4 times 10 to the minus 7th meters. If you remember, the choices we were given were all in nanometers, so we're going to have to convert to nanometers. 4 times 10 to the minus 7th meters would equal 400 nanometers. And make sure you're comfortable doing those sorts of unit conversions on an exam. So if we look at our three choices, that would be choice A, 400 nanometers would be the correct answer. Okay, here's a second review question. And this one you don't necessarily have to do any calculations. So it's concerning the photoelectric effect. And when a photo of red light at 650 nanometers hits metal X, an electron is ejected, shown here. Will an electron be ejected if a photon of yellow light, wavelength of 570 nanometers, hits the same metal? So to answer this question, we don't have to do really any calculations. All we have to remember is the equation for the photoelectric effect, and that is kinetic energy equals h nu, so the energy of the light that we're shining on the metal, minus phi, or the work function for that metal. Now if we look at both, we'll call this h nu for the red, and we'll write this equation again in terms of the yellow light, h nu, yellow minus phi. Now phi is the same in both instances. It's the same metal, so the work function is the same. But the first light is red, so it has a longer wavelength, which means it has a shorter frequency. Excuse me. Yeah, that's correct. Sorry. It gets confusing. So it has a smaller frequency, so its energy is less than the yellow. But we know that even though red light has lower energy than yellow light, we're still getting an electron kicked out. So the question is, will an electron be kicked out if we use yellow light? Yellow light has a shorter wavelength, so a higher frequency, so the energy is higher of this light. So if red light, which is lower energy, kicks off an electron, that means, yes, yellow light will also kick off an electron from this metal. Yeah. So the real key here is to recognize, to think about the light in terms of energies. So the photons from yellow light have more energy than the photons of the red light. Here's a similar question. If a photon of blue light hits a metal X and an electron is ejected, will an electron be ejected if the same metal is hit with green light this time? Again, we need to use the equation for the photoelectric effect. So this time the energy of blue light is higher than the energy of green light. And we know an electron is kicked off when the blue light hits the metal. Can we tell if an electron will be kicked off when the green light hits the metal? And the answer is no. We're given no information about what the actual work function is, phi, for this metal. So we have no way of telling if the lower energy green light is going to be able to remove that electron. We don't know what the minimum frequency required is, so we can't tell. Again, whether or not a green photon will eject this electron will depend on how tightly the electron is bound to the metal, or, in other words, the work function for that metal. And we're not given that in this problem, so we simply can't answer this question. Okay, the last review question we have: for which of the following species is the Bohr model applicable? So think back to the Bohr model. It's for hydrogen, but what other species can it be applied to? And if you look closely And remember that the Bohr model only works for one electron, atoms or ions with one electron. The answer would be 3, lithium 2+. Helium has 2 electrons. Beryllium plus would have 3 electrons. Beryllium usually has 4 electrons, but that plus sign indicates we remove one. Hydrogen minus, neutral hydrogen has 1 electron. Hydrogen minus is going to have 2 electrons. So that leaves us lithium, which normally has 3 electrons. If we remove 2, we get a positive 2 charge, and it's left with only 1 electron. And we're going to talk a little bit more about ions today. Moving on to Chapter 8. The first thing we're going to talk about in Chapter 8 is the property of electron called spin. That's in Section 8.1. Then we're going to go through electron diagrams, writing electron configurations, and how that corresponds to the periodic table. That's Section 8.2. And I would highly recommend that while you're going through this lecture, you keep a copy of a periodic table close to you, because everything will make much more sense when you view this with the periodic table. And finally, Section 8.3, we're going to talk about trends in atomic properties, and most importantly, our size and ionization energy. And there's some important exceptions to the trend of ionization energy that we're going to talk about. Well, we saw that in Chapter 7, Bohr's model for the hydrogen atom. It described the hydrogen atom very well. And we also talked a little bit about Schrödinger's equation and how it can be solved and it yields quantum numbers. Well, Schrödinger's equation can be solved exactly for the hydrogen atom, and that hydrogen has 1 electron and 1 proton. Some of the problems with the Bohr model that we've seen is that it can only account for atoms with 1 electron. And Schrödinger's equation, it can be applied to multi-electron atoms, but it can only be solved exactly for hydrogen atom. It gets really complicated, and the Schrödinger's equation is shown here. You're not going to need to ever use this in this class, but I just showed it here just as an illustration of how complicated it is. So it turns out that electrons have, there's another quantum number, and that is dealing with what we call electron spin. And this was discovered when some scientists shot a beam of electrons through a magnetic field, and they noticed that the beam was bent up and down, meaning that one group of these particles was being attracted by the magnetic field, the other group was being repelled. And what does that look like if we try to vision this electron? Why do we call it spin? Well, it's a charged particle, and if it spins on its axis, you remember, we talked a little bit about this in terms of electromagnetic radiation, how there's an electric field and a magnetic field perpendicular. So if this electron is spinning on its axis, it creates a magnetic field. And it can either align itself with the external magnetic field or against an external magnetic field. And if we vision the two spin states, we can call them up and down. In the absence of a magnetic field, they have the same energy. But when we apply a magnetic field, B naught in this direction. That's the external magnetic field. We see that the plus 1/2 spin orients itself with the magnetic field, so its energy actually lowers. And the minus 1/2 spin state is aligned against the magnetic field. Its energy increases. So now we can say we have the full set of quantum numbers. We learned about the first three last time. That is, the principal quantum number describes the orbital energy or the orbital size. The angular momentum quantum number L, and this describes the orbital shape, or I like to think of it as the type of orbital. And this is a good chart to illustrate that. The L values 0, 1, 2, and 3 correspond to s orbitals, p orbitals, d orbitals, and f orbitals. The last one we learned about previously was magnetic quantum number m sub L, and this is the orbital orientation, or really it is the description of which orbital you're in. And finally, now we have the quantum number m sub s, and that is the electron spin. It can be plus 1/2 or minus 1/2, and this is the direction of the electron spin. So each electron in an atom is described completely by the full set of 4 quantum numbers. The first 3 quantum numbers describe the orbital. The last quantum number describes the specific electron. Pauli's exclusion principle, you might have heard about that previously. This principle states that no 2 electrons in the same atom can have the same set of 4 quantum numbers. And another way to put that is that each orbital can only have a maximum of 2 electrons. And these electrons in the same orbital have to have opposing spins. Let's talk about some factors that affect atomic orbital energies. The energies of atomic orbitals are affected by, 1, the nuclear charge, which we call Z, and shielding by other electrons. Electrons are negatively charged, they repel each other, but there's an attractive force between them and the positively charged nucleus. A higher nuclear charge increases that nucleus-electron interactions, and that tends to lower the sub-level energy. Shielding, on the other hand, reduces the nuclear charge that the electrons experience, and that leads to what we call effective nuclear charge, or Z effective, and that's the charge from the nucleus that the electron actually experiences. And then the final factor affecting energy is the orbital shape. So the actual shape of an orbital affects its energy. So if we look at figure 8.2, this is the effective nuclear charge on a sub-level energy. So the greater the nuclear charge, the lower the sub-level energy. And we can see that using this example. Hydrogen has a positive 1 charge, 1 proton in the nucleus, 1 electron. The energy level, the energy required to remove this electron would be negative 1311 joules. Now if we look at helium plus, so that's a helium atom with 1 electron removed. Helium has 2 protons in the nucleus, so it has a positive 2 charge. That 1 electron now experiences twice as strong an effective nuclear charge compared to hydrogen, and it is much harder to remove. So it would take 5,250 joules of energy, kilojoules, to remove that electron. And as you'd expect, lithium, if we look at lithium 2+, that would be a lithium atom with only one electron. A lithium has 3 protons, so a positively 3 charge in the nucleus. And to remove that one electron, it would take 11,000 kilojoules, almost 12,000 kilojoules. So nuclear charge lowers the sublevel energy. Okay, now let's talk about electrons. That was just for the case with one electron. What if we have more than one electron in the same energy level? Well, electrons in the same energy level, the same principal quantum number, shield each other to some extent. And if we talk about electrons in lower energy levels, that is orbitals with lower principal quantum numbers, these inner energy level electrons shield the outer electrons very effectively. And this really lowers the effective nuclear charge that an outer electron experiences.